All right, good morning, guys. This is Mr. Ayodeji again, aka David Max, and I'm back again with another video on dependent probability. Dependent probability. That'll be our next topic. So let's get straight into that topic very quickly. When it comes to dependent probability, we are going to be learning how to deal with events that has to do with doubt replacement. Selection without replacement. Okay, we're going to compare independent and dependent events to see how they link together. And then we shall be calculating probability of dependent events. And then we can also look at the use of probability trees. Okay, all right. So in today's class, please let's remember to pay attention to the lesson very quickly. So we go right straight into it. Now, let's quickly recap some probability vocabulary and notations we have been using since the beginning of the topic, probability. Suppose you have a bag of two colors of marbles, yellow and blue. You can see that in the bag right here, yellow and blue. We reach in to the bag and choose a marble at random. Now, when we choose at random or we select at random, it means that we are not looking. Okay, it's just without looking. All right, you're picking at random, you're choosing at random, you're selecting at random. Now observe the color and then replace the marble. This is a trial or an experiment. So you can see the word trial, experiment means the same thing. There are two outcomes, definitely, for this experiment. Those two outcomes are, it's either the marble is blue, that's one outcome. The second outcome is the marble is yellow. Now, an event is the outcome of a trial, okay? An event is the outcome of a trial. So let's call the event, the marble is blue, and the event, the marble is yellow. Okay, so the probability of B, so are you getting that now? We call the event marble is blue B, and we call the event marble is yellow Y. So the probability of B, we write as P bracket B, remember that? And similarly, the probability of Y, we write as P bracket Y. I'm sure we all remember that by now. Now that we have our vocabulary, let's go on with the experiment. Suppose there are 3 yellow marbles and 4 blue marbles. This is a new bag now. We have 3 yellow marbles and 4 blue marbles, okay? The probability experiment is to reach into the bag, observe the color, and replace the marble. Then you are going to find the probability of Y and probability of B. Remember, probability is a ratio of successful outcomes to total outcomes. Remember, I also told you that the successful outcomes here, in some cases, we can also call it required outcomes. Exactly what the question is talking about, or what the question is asking us to find its probability. It's also the success. Anyway, now 3 are yellow, so there is a 3 out of 7 chance of choosing a yellow marble, and there is also a 4 out of 7 chance of choosing a blue marble. So probability of Y is 3 over 7, and probability of B is 4 over 7. I think that is very clear. We already understand that. So it is often helpful to put these into a probability tree. Each branch is an outcome, remember that? So it starts from here, the first branch for the first outcome, second branch for the second outcome. So the probability is written on the line, okay, which is the branch that we're talking about. On this line too, the branch 3 over 7 there for yellow, and then 4 over 7 as a probability for the blue. Okay, so this section from here to here of the tree represents one trial. So that is just one trial that has been represented there. So I think this is really very clear, no big deal. We move on. Now let's look at what happens if we do the experiment 2 times in a row. Trial 1, what is the probability that the marble is yellow and then blue? So yellow is 3 over 7, we have that already. Blue is 4 over 7, We have that already. Now in trial 2, what is the probability that the marble is yellow and then blue? Now nothing has changed because the marble was replaced. It is the same as trial 1. Guys, think about this. You have to understand this about replacement, okay? Because when you are performing an experiment, you pick and then you replace, you pick and then you replace, it means nothing happens, okay? Nothing changes. Please take note of that. So the probabilities you'll be using for your outcomes will remain the same because you were returning them back when you were picking. So in the second trial, the probability of Y and the probability of B will remain the same, 3/7 and 4/7 respectively. Now let's draw a probability tree to represent the two trials. So we have 3/7 on this branch for Y, and then we have 4/7 on this branch for blue. That's for B. Now, for the second trial, remember what I said about this? You are supposed to bring out 2 branches from here and 2 branches from here as well, okay? From the 2 outcomes of the first trial. And that is how that is meant to be. So let's take a look at that exactly. All right, so for the first yellow, over here, you have 3/7, yellow here too is 3/7. You can see that in the second trial, the probability of getting yellow remains the same 3/7 as it was in the first trial. That is because in the first trial, we replaced back, okay, the marbles. We didn't keep them to ourselves. We put them back in the bag. So probabilities remain the same. And also for probability of blue as well, it remains the same. Now, what is the probability that the marble is blue on the first trial and yellow on the second trial? Blue and yellow. The first trial, this is blue, and the second trial, yellow. So this is yellow. So you have to follow the 3 branches. First, blue in the first trial. Then moving into the second trial, you follow from that blue and follow the branch that goes to yellow. So on those branches, we have 4/7 and we have 3/7. So it's going to be 4/7 times 3/7. I'm using times because this is the word and. So it is the and rule that we're going to use, okay? And definitely the 2 events are independent of each other. So we are free to go ahead to use the multiplication to solve our problem. So we might write it as probability of B, Y, but I don't like that so much. I prefer the word and, so that we can write it as probability of B and Y, B and Y, so that that word and can always remind you that you are dealing with multiplication. So preferably, please guys, write it as P bracket B and Y, okay, so that it gives you clarity on that. So this is going to be 4/7 times 3/7, which is 12/49, okay, and that is how that goes. So just like I said, let me just quickly put this. I would like you guys to stick to this notation instead of the comma. Write it as probability of B, okay, and then use the word and in between it, B and Y, and that will be equal to the probability of B, close bracket, multiplied by the probability of Y, this way. So let's maintain this kind of notation. So guys, stick to this, stick to this, stick to this. Very, very important. Stick to this, right? Leave the comma, don't use commas, okay? You are better understanding this using the word and to express that this goes for multiplication. So moving on. Now, when the probability of the combined event can be written as a product of the probabilities of each event, I mentioned it earlier on, the events are said to be independent. In plain language, 2 events are independent when they do not affect each other. Moving on. Okay, we're going to change the experiment slightly, guys. Suppose that now we take a marble, observe the color, but do not replace it. Now we're going into another section. The first section we talk about replacement. We were replacing it. And what happened? The first trial, we picked, we replaced. In the second trial, because we replaced, the probabilities will not change. The number of marbles in the bag will remain the same because we replaced the one we picked at first. Okay, so nothing changes. But when it comes to the event whereby you do not replace after picking the first or the second or whichever level we are going, let's see what happens. The first trial, what is the probability that the marble is yellow? Of course, that is 3 over 7. We know that already. How about when it is blue? Of course, 4 over 7. We know that already. Let's go to trial 2. What is the probability that the marble is yellow? Now, this trial 2 depends on the outcome of trial 1. There are 6 marbles left in trial 2. You can see what has happened there. Initially, we had 4 blue marbles. But because when we picked the first blue from the first trial, we did not replace it. So the number of blue balls has reduced by 1. We now have 3 blue balls. And at the same time, the total number of balls in the bag has also reduced from 7 to 6. So please take note of that. That is the most important thing to remember when you are dealing with events without replacement. Okay? What you picked would have reduced by 1, and the total number would have also reduced by 1. All right? So, probability of Y, if the trial 1 was that you picked the blue, would now be 3 over 6. Because the number of blues now has reduced to 3 from 4, and then the total number of balls is now 6. So 3 over 6. Now, if it was, okay, we are still dealing with picking B first. The probability of blue now, oh, sorry, the first, it was probability of Y at first, which we will have 3 yellow balls. So definitely 3 over 6. But probability of blue now, just as I explained before, after taking a blue marble out, is now 3 over 6, no more 4 over 7. Because the 4 blue marbles has reduced to 3, and the total number of balls has reduced to 6. You see that even the probability of Y is not 3 over 7, as it was in the first trial. It is now 3 over 6, okay? All right, please take note. You will see that the number of yellow balls that we had in trial 1 still remains 3 also in trial 2. And that is simply because we did not pick a yellow marble. It was a blue marble we are talking about, that if we have picked at first. All the yellow still remains complete. It was the blue that reduced. Okay. Now, what if it was yellow that was picked at first? What would have happened is that the total number of balls would have also reduced by 1, so we have 6, but the number of yellow marbles would have reduced by 1 as well. So no more 3 yellow marbles, but 2 yellow marbles now. So that is why the probability of Y in the second trial is going to be 2 over 6. Likewise, the probability of blue in the second trial will be 4 over 6. Blue did not reduce. So it's now 4 over 6 for blue. Okay, guys, let's draw a probability tree to represent the 2 trials. So you have first 2 branches. Probability of Y for the first trial is 3 over 7, 4 over 7 for blue. Okay. In the second trial, see what happens. Aha. Can you see it now? Probability of Y is 2 over 6, of blue is 4 over 6 in the second trial, because in the first trial, or the first trial was done without replacement. Was done without replacement. So it has affected the probabilities. There's a change. Okay. All right. So therefore, this is what we have. So for trial 1, when it was yellow that was picked at first, the probabilities of picking yellow and blue again, okay, because we did not replace that first yellow that was picked, are 2 over 6 and 4 over 6. And for the second trial, which is for B, right here, meaning that it is B that we picked first and we didn't replace, the probabilities of Y and B are 3 over 6 and 3 over 6 respectively. So put that into the probability tree as you have seen it in that diagram. Very, very clear. Okay. Now to now calculate the probability of B and Y, remember I said this comma here, I prefer you to be using the word and, so that for clarity, B and Y, you just need to multiply the probabilities along the branches of the tree. So this is B and this is Y. B and Y. B and Y. So you have to multiply 4 over 7 by 3 over 6 this time around to get a probability which is 2 over 42 and can be reduced actually. So are these events independent? Of course not. They are not independent. Okay. This is now what we call dependent events, guys. Why do we say they are not independent? Okay, that is simply because what happens in the second trial depended on what has happened in the first trial. Okay, because we discovered that in the second trial, that means the second time that we are picking the ball, there was a change. Okay, if it was blue we picked at first that we did not replace, the number of blues had reduced and the total number had reduced. Also, if it was yellow we picked at first in the first trial, in the second trial, number of yellow marbles has reduced and the total number of marbles in the bag has also reduced. Okay, so we call this kind of event dependent events. Okay, events that are not independent are definitely dependent. In plain language, two events are dependent if they affect each other. Okay, so there's a way, even in a situation where you have actually independent events, because the event of doing the first trial and then doing the second trial is actually independent of each other. They are not supposed to affect each other. But when you now put a condition, okay, condition of don't replace, without replacement, that condition changes the independency to dependency, because what happens in the second trial would have been affected by what happened in the first trial. Moving on, guys. We can then try to do this class activity, okay, on our own. Try to drag this into whether it is dependent or independent. You can see the probability of A, probability of B 0.5, probability of B intersection A is 0.25. Intersection means that you're talking about, okay, the outcomes that we are talking about. Okay, it could also mean and when it comes to independent events. So we can choose to drag it in here like that and drop it, and then we'll move. This is probability of A and B equals the probability of A plus probability of B. Of course, definitely this works for independent events. And then we have probability of, okay, A intersection B is actually 0.5. It's supposed to be 0. So we could choose that to be in dependent events. And over here, we can have, let's see what we have already. So this is out, okay? We need to drop it here for, so you can see that this is correct where they are, okay? And the probability of A and B, probability of A plus probability of B dependent events. Oh, what for independent as well? Oh, plus, okay, plus, yeah, that's dependent, definitely. Dependent, like the OR root, so this is supposed to be like the A or B. That's why we have addition here. But this is multiplication now. Probability of B, probability of A. This is a product, so that means this goes for independent events. So mark it, that is correct. So we have more to go on, but then I think you figure out what we're talking about here. So let's move on. Over here, we want to see how we can use a drawer full of black and white socks. Now there are 24 black socks and 29 white socks. You pull 2 socks out at random, okay? Now, guys, take note of this. What they mean here, so that we can have a proper understanding of what we are dealing with, by saying you pull 2 socks or you pull 2 socks out, okay? They've gone beyond telling us that it was done with replacement or without replacement. But take note, guys, the questions I'm going to be asking you will definitely identify whether it was done with replacement or without replacement. You need to take note of those two things, with replacement or without replacement. Now, when you pull 2 socks out, pulling and then the word out, it means that you are not returning. When you pull something out, it means you are not returning it. You pull it out. So in other words, that statement actually, or the phrase there actually means that you did this experiment or trial without replacement. So that simply means that we are dealing with without replacement here now. So take note of that, guys. All right. So let's move on. Now, the probability of B and B. But first of all, before we come to this, let's fill in the probability tree, first of all. And to do that, we all know from previous knowledge that we are to add 24 plus 29 to get the total number of socks, okay, in the draw. And if you add that together, you should get 53, okay? 53 for that. So that means that for my first trial, I'm meant to have the total number as 53. The probability of drawing or pulling out a black socks is definitely going to be 24 over 53. And the probability of drawing out a white socks should be 29 over 53. Remember, we are pulling out, which means we did not replace, without replacement. Now, coming to the second trial, that means the second socks you want to pick out. This was for the first socks. Let me try to box that out. Okay, this was for the first socks. Okay, this aspect is for the first socks. Okay, so because of that, since that's for the first socks, for the second socks now, something has happened during the first picking of the first socks, guys. We did not replace that first socks. It was done without replacement. So because of that, one socks is out. So that means that at the time when we picked the black socks, the total number of black socks has reduced because we didn't replace that black socks. It has reduced to 23. So this is going to be 23. And then the total number of balls in the draw is no more 53 as well. It has reduced to 52 because of that one black that was removed and was not replaced. Now, if I'm to pick a white socks, remember it was a black socks that was picked and was not replaced. So the white socks did not reduce. It was the black that reduced. So the number of white socks will still remain 29, but the total would have still reduced to 52 because of that one black that was not replaced. Let's move to the next one. Now, in the case where it was a white socks that was removed in the first place, okay, by the time I want to pick a black socks, black will still remain 24, but the total would have reduced to 52. If I'm now to pick a white the second time, the white would have reduced because it was white I picked in the first place and I didn't replace. So the white would have reduced to 28, while the total of socks in the draw would be 52. Okay, I believe that is very clear and that is all correct. Oh, let's check. Okay, I see where the not all correct is coming from. We still have more to do. That's why I said not all correct. So let's come back here now. The probability of blue and blue. Of course, we have to follow. Okay, so let me box this out too. This one right here. To show, okay, not there. Just to show for the second trial. So this is first trial, second trial. Now, please, for us to know the probability of blue and blue, remember I said that comma goes for blue because we are dealing with this kind of event, blue and blue. That is, the first socks we picked is blue, and the second socks we pick, I'm saying blue, sorry guys, black, and the second socks is black. So black and black. So that means that I'm saying I would have preferred to write this as P bracket B and B for clarity. And if I follow through with black and black, this is black and black. First black and black in the second trial. Remember, and goes for multiplication, so the probability will be 24 over 53 multiplied by 23 over 52. Okay, please take note of that. 24 over 53 multiplied by 23 over 52. So when you multiply that, you're going to get 138 over 689. 138 divided by 689. Okay, let's mark that. That is correct. So you see how it's going now. If I'm to do probability of white and white, first white and second white, I will come here. This is white in the first trial, and this is white in the second trial. So that is 29 over 53 times 28 over 52. 29 over 53 times 28 over 52. Okay, and that should give us 203 over 689. 203 over 689. That's for this one. 203 over 689. So mark that. That is correct as well. Now, the probability of match. What do they mean by match? Now, by match, they mean that, okay, this is a match, black and black, and this is a match as well, white and white. Okay, so when they say probability of match, what they mean in essence is simply that you have to find the probability of black, probability of, let me put a big bracket. So it's going to be black and black, close bracket, or we have two different possibilities of having matches. Black and black is a match. White and white is also another match. So this is what they're talking about. So we need to find this probability. Okay. But of course, you know that this can further be expressed as probability of, okay, let me use it from here. Probability of black and black, like this, then close it. Okay, I can even decide not to use it. Yeah. Black and black. The OR takes us to addition, plus the probability of also white and white. And then you close it. So definitely to run with this, we all agree that what we are to do is just to put the value of this and add to the value of that, because OR means addition. So if we add together black and black, and we add it to white and white, we're going to have, we're adding to, okay, 138 divided by 689. It should give us 341. Okay, 341 when we add that together. So this is 341 divided by 689. I think this is very, very clear, and that is correct. Well done, guys. So you can see how this is going. Very interesting. You just have to understand the process and get it over with. Okay, so that is that. Moving on. Over here, you can see what I have here. There are 3 cards labeled 1, 2, 3. Choose one card at random. Then without replacing the first card, choose another card at random. You sum the cards. What is the probability that the sum is 3? Okay, of course, we need to tick the box underneath the tree diagram with the correct shape. Okay, there are 3 cards. We choose one, we did not replace. So since we are choosing one out of 3 cards, we only have 3 outcomes. And the 3 outcomes, remember that what we are supposed to write here are the outcomes. Okay, and since the number of outcomes is not much, I think we can just go for this so that we have all the outcomes out. 1, 2, 3. Outcome 1, 2, and 3. We can have that. You know, in some cases, when you have a certain number of balls in the bag, or a set of playing cards, and you want to talk of spades, you can't just write out all the cards one by one, 52. Okay, But this one is so small, so we can just go with 1, 2, 3. And then since we are picking one by one, and then remember that the second time we are also picking a card. Okay. But then the first card that was picked was not replaced. So since we are saying we want to choose all the outcomes 1, 2, 3, that means that the second time that we are picking, we will only be left with 2 cards to pick from. Okay, because the first card was not replaced. So I think I'll go with this. And that is correct. So let's move on. We want to fill in the 3 diagram for choosing the cards. Okay, remember what the cards was about? The first card is card 1, the second card is card 2, the third card is card 3. Just understand the 3 diagram much more. That's why I'm doing this, guys. If card 1 was picked and was not replaced, I will only be left with card 2 and card 3 to pick from. If card 2 was picked and was not replaced, I will be left with card 1 and card 3 to pick from. If card 3 was picked at first and was not replaced, I will be left with card 1 and card 2 to pick from. Now, in the picking of card 1 from 3 cards, the probability is definitely 1 over 3. That's 1 out of 3. To pick a 2 out of 3 card as well, probability is also 1 over 3. To pick a 3, the 3 out of 3 cards, 1, 2, 3, that is also 1 over 3. Now remember here, to come here, the card labeled 1 was not replaced. So now you are picking from card 2 and card 3. That's what you have left. Okay? So because that's what you have left, the probability of picking is going to be definitely either you are picking 2 or you are picking 3. It's going to be 1 over 2. Okay? And definitely also 1 over 2. Because there are 2 cards remaining. Okay, so your probability of picking whether 2 or 3 is definitely 1 over 2, 1 out of 2. And the same thing happens for others, the same explanation for them. It will also be 1 over 2 all through like that, and 1 over 2 here as well. The market, we have it all correct. Well done. Moving on. Now, fill in the sums next to the diagram. When we talk about the sums, we mean you picked 1 in the first trial, you now pick 2 in the second trial. So the sums is 1 plus 2, which is supposed to give 3. Follow the branches, 1, 3, that should give 4. 2, 1, 3. 2, 5. 2, 3, 5. 3, 1, 4. And then 3, 2. That's the sum of 5. You mark that, you have it all correct. Well done. I believe that is clear to everyone. Now, how do we represent the sum is 3? The probability of the sum is 3, we write it this way, P bracket sum is 3, equals to the probability 1 and 3, because it is 1 and 2. You can see that 1 and 2 give a sum of 3, 2 and 1 give a sum of 3. Like I said, I would have preferred to write this using the words and. Guys, remember that. So, why are we using plus? Because it is either this one, 1, 2, that gave the sum of 3, or 2, 1 that gave the sum of 3. So the or there changes to addition when we split out the probability. So of course, the probability of 1 and 2, okay, is the multiplication of 1 over 3 times 1 over 2. Okay, please take note of that. I would have really, really loved to show us how that would have worked, okay? Which I would have preferred to say that so that we don't mix it up. What we would expect, let me put it here under here, is for this to be, we'll have this to be equal to, let me just continue with what they've written. Remember, I'm choosing and, so it's going to be 1 and 2, that's 1 over 3 times, so I'm going to put it in bracket, 1 over 3, for clarity, pardon me, 1 over 3, I mean, then times, the next one is 1 over 2, close the bracket. That's for probability of 1 and 2. Then plus, bracket open, probability of 2 and 1, it will be 1 over 3 times 1 over 2 as well. Showing you that's right here, 2 and 1, 1 over 3 times 1 over 2. So take note of that. So it's going to be 1 over 3 as well, times, okay, 1 over 2, bracket closed. So that's what you do to give you the answer you are looking for right here. So if you multiply this, you should expect to have 1 over 6, and here also 1 over 6. And then when you add them together, you expect to have 2 over 6, which is 1 over 3. And you mark that all correct. Well done. So guys, that is how this goes. Very, very interesting. Moving on. We have a biased coin, which lands on heads 29% of the time and tails 71% of the time. You flip the coin 2 times and record the results. The flips are independent. Now fill in the probability tree and use it to calculate these probabilities right here. Okay, as I've explained, I'm sure that you can follow through and answer this question. You know that a coin, we have only 2 outcomes for a coin. Either it is a head or a tail. So we have head, tail, okay? Remember that head, tail will still remain here as well, because head and tail will always remain on the coin. There's no replacement or no replacement here. It's not as if we are picking from a bag. We're only tossing a coin, okay? So remember that. So very quickly, so that we are done with this, what do we have here now? Of course, for a head, it's always 1 over 2. Tail, 1 over 2 as well. Okay, the second time, what's going to be for the second time? Okay. There's a condition here that we need to look at. Is a biased coin. We are dealing with a biased coin, guys. So which means the probability is not going to be half-half. Okay, the half-half we are talking about here is for a fair coin, the unbiased coin. But this one is biased. So 29% of the time, that means we need to find the probability here to get what we're going to have as a fraction here. So if I'm going to go with it straight away that way, for heads it's 29 over 100, so we'll put it this way. And for tail is 71 over 100, that's 71%. So in fraction, we have it that way. If you mark it, both correct. So let's keep going. So the second time, because you did it 2 times, the second time you pick the head, remember that there is no replacement without replacement here, okay? The head and the tail remains on the coin. So when you roll again, we still have the same chance that it will land on head 29% of the time as well. So for head here, we're still going to have the same 29 over 100. Likewise, for tail, we're going to have the same 71 over 100. If you mark that, you have them both correct. Same thing happens here as well, because nothing is changing in this case. Still 29 over 100 for head, and also 71 over 100 for tail. And that is correct. Now, when it now comes to probability of tail and head, this is tail, this is head. So tail and head will be 71 over 100 times 29 over 100, okay? Times that, so you have, that should then give you 2059. That should give you 2059. Okay, divided by, when you multiply all of this, 100 times 100 should give you 10,000. Okay, you took it. Then the next one, probability of head and tail. So you come for head for the first trial, tail for the second trial. So that's 29 over 100 times 71 over 100. Okay? So we have 29 over 100 times 71 over 100. Okay? Oh, it's actually the same thing. So it's also 2059 over 10,000. And finally, to have a match is going to be head and head or tail and tail. Remember that? Head and head or tail and tail. So for head and head, we have 29 over 100 times 29 over 100. That's for head and head. 29 over 100 times 29 over 100. And that gives 551 over 10,000. So we're going to have this, let me put a text in there. We're going to have this to be equal to head and head. It's going to be equal to, just for clarity purpose, so that we can all follow, head and head. Or the all changes to plus probability of tail and tail. That's for the match, tail and tail. And that means we have that to be equal to 29 over 100, okay, in bracket, times another 29 over 100, okay, then plus tail and tail. For tail and tail, that's 71 over 100. I'm sure you will follow through, times 71 over 100 as well, tail and tail. Okay, so all we just need to do is to simplify that to give us 551 over 10,000. Okay, 551 over 10,000. Then plus 71 times 71 over 100 over 100 times 71 over 100. That's 5041. That's 5041. Also divided by 10,000. Okay, so that is that. So when we add that together, okay, 29 is actually 841. I'm checking that again. That is actually 841 here. 841 for head, 29, 841. So when we add that together, we are just simply going to have to add it to 5041. 5041. To give 5882. 5882. So final answer here will therefore be 5882, okay, divided by 10,000. Fantastic, and that is very correct. Well done, guys. So that is how that goes. So, rounding up, the probability of passing P, a driving exam, with lesson L is 0.83, and without lesson L is 0.45. 58% of students take lessons. Okay, moving on. A student is selected at random. Fill in the probability tree and use it to calculate these guys here. If you have to fill in this, remember that their own prime here means complement, okay? And it actually means not, okay? Not L. We used to use bar instead of the prime. We use bar on top, remember that. Bar P, P bar P, P bar P, L bar L. That is with lessons and not with lessons. That's what they call without lessons there. Okay. Remember they said that the probability is 0.45 and it is 0.43. Okay. So you fill in this, 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 fill in this. I want to believe that you guys can actually work this out. So take a look at it with all the lessons, all you've learned already. Look at it very well, okay? And try to fill in all these values by yourself. All right. I believe you'll be able to get it based on the explanations that we have been given so far on this topic. So thank you guys. That will be all for this particular video. Make sure you like, comment, and subscribe, and I'll see you in my next video. Thank you very much. Thank you so much. See you in the next video, guys. Bye for now.